Hi, and welcome to the Consulting Specifying Engineer webcast, Understanding HVO Fuel and Gensets, sponsored by MTU, a Rolls-Royce solution. I'm your moderator, Gary Cohen. Happy to join you today on behalf of Consulting Specifying Engineer and CFE Media. So before we get started, here's some tips to help you get the most from today's webcast. If you are experiencing issues with your slides or audio, simply refresh your browser or click the Refresh Media button directly under the presenter's picture. You can control the volume of this webcast by adjusting the volume on your computer or by adjusting the volume on the webcast platform. If you're having any technical problems with the audio or the slide presentation, just click the question mark at the top right corner of your screen to access a list of system checks to try before contacting an online technician. But if you actually do need a technician, type a message in that Ask a Question box and someone will get to you as quickly as possible. Individual technical questions will be answered in the Answered Questions box. If you have questions for the speakers as the presentation goes on, you can also put those in the Ask a Question box on the left side of your screen. The live Q&A session will begin after the presentation concludes. Today's webcast is being recorded, and you will receive an email within a week with a link to the on-demand event. To download a certificate of completion and a PDF copy of the presentation, use the Event Resources tab on the left-hand side of your screen. Those documents will also be available with the on-demand version of this webcast. Now, again, before we get started, we will hear from today's sponsor, MTU, a Rolls-Royce solution. At the conclusion of the video, you may experience a few seconds of silence. That's just to compensate for varied internet speeds. Please stay tuned after the video for today's presentation.
Ever wonder what our life in the future will be like? Say in the year 2050?
We see a world powered by sustainability, powered by very clean energy.
How can we design CO2 neutral and cost-efficient products? This question drives us.
Thanks to technologies that effectively reduce greenhouse gas emissions, like climate neutral drive and power supply solutions. Hydrogen is generated from electricity and electrolyzers and converted into other climate neutral fuels. Fuel cells and combustion engines use these to power ships, trains, and other vehicles. Even complete infrastructure solutions like microgrids that integrate renewables to securely deliver green energy to industrial areas, hospitals, airports, data centers, and more energy networks that keep costs and emissions low by intelligently balancing peak demands. Also, battery storage systems that store green electricity for use at a later time.
By looking at the bigger picture right from the start, we're able to develop future-oriented solutions that allow our customers to meet their net zero commitments.
Powering the path to sustainability.
Now we get to the fun part of today's event. I'm happy to introduce today's presenters, Brian Ponstein and Jens Engelhardt. Brian is responsible for the entire 60 Hz stationary product portfolio for Rolls-Royce Solutions. He's been in the power generation and backup power market for more than 15 years. Brian earned a Bachelor of Science in Heavy Equipment Service Engineering and a Master in Business Administration from Ferris State University, Big Rapids. Brian has written several articles and is an author for the 5th edition of the EGSA On-Site Power Generation, a reference book. Brian has been a keynote speaker at several conferences within the power generation market. He's also worked overseas in Germany, supporting the global power generation market from both a sales and engineering perspective. Brian continues to challenge himself by leading multiple teams simultaneously to develop new product offerings under the MTU brand. Jens is responsible for engine calibration and engine testing work performed in the Research and Development Center at the MTU Aiken plant in South Carolina. He has 12 years of experience in engine development and engine calibration and holds a master's degree in engineering as well as an MBA. Gentlemen, it is now time for me to turn things over to you.
Thank you very much, Gary. This is Brian Ponstein, and this presentation is going to take on a conversation flow between myself and Jens to where we're going to dive through the topic of HVO. We're first going to understand and ask questions about what is HVO. Then we're going to understand why are we using HVO? What is all the hype about it? And then thirdly, we're going to get into some of the challenges, understanding what challenges are out there in the market. And then we'll wrap this up and leave some time at the end for some questions. So if you do have questions, please at any time write them into the chat function, and we'll get those answered at the end. So Jens, please help me out with this topic of HVO. What is HVO? Is it an acronym? Does it mean something? Let's kind of start at the basics, if you don't mind.
Yeah, absolutely, Brian. Happy to help you here. You're right. So HVO is actually an abbreviation. It stands for Hydrotreated Vegetable Oil. In order to talk a little bit more about why it might be a good alternative compared to our fossil fuel, we have to dive a little bit into the chemistry. I'm a mechanical engineer, I'm not a chemist, so please bear with me here. Also, should we have chemists in the audience, please don't judge us too hard. So as the name already says, the name tells us basically something about the feedstock or the raw material that's being used, and also the production process that's being used to create this kind of fuel. So the feedstock, we're talking about vegetable oil. That could be soy, that could be rape, it could be sunflower. Even better if we use the waste oils of these vegetables. So once we are done cooking with these oils, instead of just disposing them, we can recycle them and create this kind of fuel. And when we talk about CO2 neutrality, CO2 reduction, this actually has an additional advantage. We're going to talk about that later in the presentation when we talk about the well-to-wheel approach, because ultimately that is the current challenge. We're talking about decarbonization. So the goal is here really to avoid adding more CO2 emissions to the atmosphere. Whenever we talk about fossil diesel, synthetic fuels, and HVO is considered as synthetic fuels, they are always hydrocarbons. So every time we burn these hydrocarbons in our combustion engines, when we basically oxidize them, we are going to generate CO2 no matter what. So in order to avoid adding more CO2 emissions to our atmosphere, we got to look for a way to basically offset the emissions that come out of our engines with some kind of a CO2 credit that we try to get during the entire life cycle. And we're going to touch on that a little bit later as well. But of course, besides CO2 neutrality, what we also got to make sure is if we replace our fossil fuel with some other kind of fuel, that we don't see any other disadvantages. So it means we want to make sure we still get the same power, we still have the same or even lower emissions, otherwise we jeopardize our label. And of course, in terms of longevity, we want to make sure that our customer also doesn't have any disadvantages in terms of lifetime. And what we're here looking for is when we compare fuels is, are they chemically comparable or chemically different to each other? And that's what we're going to look into on the next couple slides. And I think this also leads us over to the next slide, explaining a little bit what HVO is actually not.
Yeah, you talked a little bit about how this comes from various feedstocks, and to me that sounds a lot like biodiesel. And let's talk about what it is not, how that is different. I have a feeling we're going to get into some chemistry, but let's just start talking about this from what it is not, or how it's different than biodiesel.
Yeah, so it is not a biodiesel, exactly, Brian. So it's not a biodiesel, or as we know it as FAME. You are absolutely right. It uses exactly the same feedstock, so the same vegetables, the same vegetable oils. Nevertheless, the process that produces this fuel is a different one. And the result is a chemically different fuel compared to fossil fuel, whereas our HVO is chemically comparable to fossil fuel. That's why HVO is also considered a drop-in fuel, because you can run 100% on HVO, whereas if you want to use biodiesel, you usually have to blend it with your fossil fuel. And I think just to get a little bit a better overview of all these different chemical procedures and so on, I think we have one slide that summarizes that a little bit. Yeah, perfect. Thank you, Brian. On top of the slide, you see the biodiesel and the HVO that we are just talking about. And as you mentioned, we see they're using the same feedstocks, but the chemical process is a different one. So for HVO, we use hydrogen. That's the hydrogenation process. So we add hydrogen to the vegetable oil. And besides that, the whole process also cleans the oil a little bit. That's why we're going to see later that HVO is actually a pretty clean fuel, as are all the other synthetic fuels, which has different other advantages that we're going to touch on later during the presentation. And you see that the biodiesel is using methanol, which explains why we produce a fuel that has simply different chemical characteristics. And that's why it cannot be considered as a drop-in fuel, because it requires blending. You cannot just run your diesel engine that's always been run on fossil fuel on 100% biodiesel without at least risking some kind of damage. Yeah, Brian, I hope that explains your question or answers your question a little bit, gives you an overview.
Yeah, I really like how we use stuff that we have today, just slightly use a different process to really improve things. But I know you don't want to get too much into the chemistry, but you know I'm going to make you do it. When we look at this, let's kind of compare these two and look at some of the major aspects that we look at with fuels.
Yeah, definitely. So for us in engine development, especially when we have to certify an engine, it is important that the fuel we are using also meets the specification defined by the authorities, like the EPA, for example. And the table here shows some of the characteristics of the fuels that are regulated and some important ones that are not regulated. And so later during the presentation, we are definitely going to talk a little bit about the cetane number, because it tells us something about the ignitability of the fuel. We are talking about oxidation stability. This is an indicator basically for the shelf life date of our fuels. And then also just to compare HVO and fossil fuel with our FAME, you can, for example, see here the distillation temperature of FAME is significantly higher compared to the other fuels. And also the flash point is higher, which, for example, explains some of the cold start issues that people experience with biodiesel. However, also looking at the non-regulated characteristics, one important value for us is, of course, the heating value, because it tells us a little bit how much energy is chemically bound in this kind of fuel, which we ultimately want to convert into mechanical energy. And here you can see that our HVO is actually the best in terms of megajoule per mass. So the heating value here, megajoule per kilogram, HVO is number one. Which is great, because most of the time when you look at the handbook or the spec sheet of an engine, you will see specific fuel consumption shown in grams per kilowatt hour. So here HVO definitely has an advantage. Nevertheless, if you look at the volumetric heating value of HVO, so megajoules per liter in this case, it only ranks second. And the reason simply is the density. You see that in the second line. HVO has the lowest density of the three fuels shown here, and that then also explains the volumetric disadvantage compared to fossil diesel. The reason it's lighter can also be explained by the hydrogenation process. As I mentioned before, the process itself also cleans the fuel. So it removes, for example, oxygen. There's basically no oxygen left in HVO anymore after the process, where, for example, fossil fuel still contains some kind of oxygen. So HVO and other synthetic fuels are pretty clean. They contain almost no contaminants, which is, again, going to help us with the combustion, but we're going to see that later in a little bit more detail.
So yeah, that's really important. And I want to dive into some of these topics in a little bit. But when we keep on looking at some of the chemistry, we have different carbon strings that we're looking at, and what do those strings look like, and how do they differ from I call it the three different fuels that we're kind of talking about? Let's look into that a little bit.
Yeah, I think, Brian, this is more or less the last slide of our chemistry lecture, if I'm not mistaken.
Well, we'll try to keep it there. I don't want to go back into what I remember from chemistry. I didn't care for that.
So yeah, here we are looking at chromatograms of the three fuels we're talking about. At the top, you see the fossil diesel fuel. In the middle, the biodiesel, the FAME, and at the bottom the HVO. And so that the x-axis shows is the retention times of the chromatograms, and you can see here in the middle, it already shows us, it's an indicator basically for the length of the carbon chains. And just if we compare the biodiesel in the middle to the other ones, we can see that the spikes are at higher retention times. And the chart also shows here for the biodiesel, it's usually between C16 and C20. That means that fossil diesel and HVO simply have shorter carbon chains. That is what this one message of this picture. And that helps us with the combustion, because shorter carbon chains usually mean shorter ignition delay, which is good because that's what we want. The second thing, what we can see is if we simply compare the number of spikes of HVO to the diesel fuel at the top, we can see HVO has less spikes. That simply means there is less components in HVO compared to fossil diesel. Again, basically confirms HVO is cleaner, which also helps us with the combustion, because there is simply less contaminants that can produce emissions that we don't want. Basically the conclusion here is HVO has less contaminants. HVO has slightly shorter carbon chains than fossil fuel, and in general fossil fuel and HVO definitely have shorter carbon chains compared to FAME. And maybe one thing to mention here, because it's also mentioned on the slide, fossil diesel aromatics is also a big topic. So aromatics is hydrocarbon rings, basically, that at least contain like one double bond. And this is also something that we, at least from an emission perspective, don't like in fuels, because usually they also serve as like a nuclei for PM emissions, because they are hard to crack. And so HVO has usually zero aromatics, or zero polyaromatics especially. And then also I mentioned it before, when we looked at the distillation curve or the distillation specifications, the longer carbon chains of the biodiesel also explain why FAME, the biodiesel, has worse cold start characteristics, because we simply need more energy to get the combustion started.
Why weren't you my chemistry teacher? I mean, you keep this simple, Jens. I really appreciate it. What I really like is
what I'm saying.
What I really like is this image here, and it's brought to us by Nesti. We give them credit for this, but it really gives a nice graphical or physical representation of the two different fuels when you burn them, and you can see some of the stuff that you were talking about. And it's just the differences between the fuel. The picture just says a lot. But now that we've talked about kind of what is HVO, let's dive more into why HVO. And when we look at that, we're going to talk about some of the advantages. And you hinted at some of this. And really what I'm seeing is we have these good storage capabilities, but I don't still fully understand why. So I want to talk about oxidation stability. You talked about cetane number a couple of times. I understand that that's related to ignition, improving that, and just helping out that whole combustion process. But I think there's more to unpack there. You mentioned a little bit about biodegradable, that it's less hazardous and it's just a cleaner fuel. And then lastly, you started talking about, and you really just hinted on this, the hydrophobic nature of the fuel, basically its ability to reject water. And I know from standby applications, water is one of the cruxes that we have to deal with. So yeah, let's first start off with the water content and what's going on there, and help me explain that. I really just have a lot of questions.
Yeah, I try to do my best, Brian. So yeah, we, like you said, we don't want any water in fuel. Unfortunately, there is water dissolved in fuel, and you can basically think of it like our air, right? If we measure 100% relative humidity at 70 Fahrenheit, and we have the same 100% humidity at 100 Fahrenheit, we know that the air at 100 Fahrenheit, since it's hotter, can simply store more water. It means here in the south, during daytime, we have 100 Fahrenheit, 100% humidity. During nighttime, it cools down to whatever, 80 degrees F. What happens is the colder air cannot hold as much water as the hot air, and we see that basically as condensation. So some of the water falls out. A similar process happens, exactly the same process basically happens with the fuel. As you have hot fuel and it cools down, water will fall out. And we need to try to get rid of this water because it can cause severe damage, especially to our fuel system. Now, the disadvantage of biodiesel over fossil fuel or synthetic fuels is nicely shown here in the chart at the bottom from Donaldson, and it simply shows you the capabilities, or basically it shows you how much water the different fuels can store, how much water can be dissolved in the different fuels. And you can see that the biodiesel can definitely store much more water compared to our fossil fuel or the HVO. That's why HVO, at least compared to fossil fuel, does not have a disadvantage, but biodiesel definitely is worse because first of all, we need to get that water dissolved so that it's free water, because only then we can separate it. And you can imagine the amount of water that will fall out with biodiesel. It's much greater compared to the other fuels. So you have to put much more effort in to get this water out of the fuel. And I think, yeah, you mentioned it before. I think you're going to show us also some impressive pictures from the field, what actually happens if people don't pay attention to that. But just quick, oh, no, go ahead.
So, I mean, some of the issues that we see that a lot of people are just commonly aware of is we get stuff growing in our tank. Water gives us that ability to have an environment for these fungal growth or microorganisms to start growing in the fuel. It also causes issues with our fuel components. The fuel is used as a lubricator, and if I can't lubricate, because I have a lot of water in there, I'm going to start wearing them out faster. And I'm going to see things like cavitation as well. The other thing that we can see is in a tank, it can start to rust out the tank. It's related to the water topic. It's kind of a combination of things, but we start seeing that, and that can show up either in our filters. It can start plugging our inlet lines, and we can just have a hard time getting fuel to our system. Therefore, we have to design systems with water fuel separators. That's always going to be the case to keep the water out of there. But the easier it is to get that water out, the less issues we have. So that really is going to benefit us a lot by having a fuel that's more hydrophobic. You wanted to talk a little bit more about the oxidation or the life of the fuel. What was that again on that chart that we look at?
The oxidation stability, like you mentioned, especially in power gen, sometimes engines don't run for days, weeks, months. So we want to know how long we can leave the fuel in the tank or wherever we store it before it basically goes bad. And the oxidation stability is an indicator for that. So when we look again at the chemical characteristics, or basically the drivers of oxidation, we have to look at two factors basically. One is water. We just talked about that. So now we know biodiesel is worse than all the other fuels, and HVO, since it's hydrophobic, it doesn't like water, has an advantage because there will be not as much water as compared to other fuels. And then the second one, obviously, we're talking about oxidation stability, is oxygen. So we want to avoid oxygen, and because we know if something oxidizes, it usually rusts, it corrodes, and we need to avoid that. I mentioned it at the beginning when we were talking about the hydrogenation process, that the main part of this process is to add the hydrogen atoms to the vegetable oil, but that it also cleans the fuel. And I said that basically all of the remaining oxygen in the vegetable oil is being removed so that there's zero oxygen left in the fuel. And that also explains why HVO has pretty good oxidation stability. I have to say we do not have like decades of long-term experience with HVO so far, like we have with the fossil diesel fuel, but just based on the chemistry and the science behind it, HVO must have at least the same oxidation stability as fossil fuel. And I think, Brian, you found some impressive pictures again from the field. What happens if the oxidation stability is not considered?
You know, I like my pictures. That's kind of how I roll. So what we see when we have this, when the fuel starts to oxidize, is we start seeing often deposits showing up, and these deposits often show up in like our injector nozzles and things of that sort. And I'll ask some more questions on this later, but when that injector gets these deposits on there, it becomes a little sticky. And when it becomes sticky, I don't get that performance that I need out of it. So I might not open or close the injector in the timely manner that I need. Some of the other things that we can see is really, this is getting into the extreme cases, of course, but I can start seeing these deposits show up on my filter. This is an example that Mercedes did a study on, to where you see a filter that it looks like an oily mess. But these are those deposits that have shown up. And what happens here in a truck application is a little bit different than a power gen. And just to explain the difference, in a truck application, what you see is you're constantly putting your foot all the way down on the throttle, and it just seems sluggish because I can't get the responsiveness out of it. But in power gen, what we run into the issue of is I can't actually get enough fuel to get to the power node that I need to hit. And then what happens is, unfortunately, we can't hit it. So then we generally trip out on under voltage or under frequency, whichever one comes first, and the unit comes offline, and it causes issues. And we want to make sure that we maintain that reliability. And by having a fuel that has a better stability or better oxidation stability or long-term storage just benefits us even more. So that's really what's happening there from application base and some of the stuff that maybe you have seen out there. But we talked a little bit, and it's related to this, is that cetane index or cetane number. I've heard both terms. Maybe you'll kind of help me explain what the difference is between the two, but what are we really getting at when we talk cetane?
Yeah, what we've touched on so far is basically what happens with the fuel in our application before it's actually injected into the cylinder. Now we want to look a little bit into the combustion process itself in terms of performance and emissions. And yeah, the cetane number is one of the indicators that tells us a lot about the ignitability of the fuel. So here, in case of our diesel engine, it's compression ignition. And what the cetane number really measures is the time difference between injection and start of ignition. So this is what's called ignition delay, and this is what's being measured. The higher the number, the shorter the ignition delay. Also, of course, the lower the number, the longer the ignition delay. And quickly going back a little bit to the chemistry lesson, I mentioned before that the HVO has nice linear, straight, single bond hydrocarbon chains, whereas especially the biodiesel doesn't have linear hydrocarbon chains and also has some double bonds that just has an adverse effect on the combustion efficiency. And you can see that here in the picture below, provided by Neste. The lower one shows the HVO, nice, straight, linear, 90-degree angles, and no double bonds. And on the top, we have the FAME with, I think the red ones are the molecules with the double bonds. So this again explains why HVO and in general synthetic fuels have pretty high cetane numbers. So our average gas station diesel, if we think back about the specification we just looked at, the ASTM D975 defines a minimum of 40. What we usually see, I would say, in the lab, the gas station diesel that we use is somewhere in the high 40s to mid 50s, which I would consider a good diesel fuel. So compared to that, HVO and other synthetic fuels are in the 70s or even higher. So that tells us in terms of ignition delay, these synthetic fuels must be better, so shorter ignition delay. And again, that is explained by the chemistry. They are cleaner, shorter carbon chains, linear carbon chains. They just ignite better. Okay, why is that actually important? It is important because if the opposite happens, if we have a long ignition delay, it can cause massive problems, leading even to catastrophic failures. And it also has an adverse effect on emissions. So Brian, what you can see here is not an HVO fuel. I just took two diesel fuels with two separate cetane numbers just to explain the ignition delay a little bit. The top chart shows the heat release of the both fuels, and the bottom chart shows the pressure traces of these two fuels. And so what you can see if you look at the top chart where the arrow is pointing at, the red curve, the fuel with the higher cetane number, so assuming better ignitability, you can see the pressure rise, the heat release starts earlier. If we look at the x-axis, I would say it's at around -8, -11, -12 degrees crank angle. And if we look at the orange one, it simply starts later. I mean, the graph here says there's a difference of about 1.5 degrees. That just tells us that the diesel with the cetane number of 50 starts igniting earlier. So this is the same load point, same parameters, same everything. So it means we inject at the same point of time, we have the same rail pressure, everything. So now what happens with the orange, in case of the orange fuel compared to the red one, is while the red one already starts igniting at -12 degrees crankshaft angle, in case of the orange fuel, we still keep injecting for another 2 degrees. That means the amount of unburned fuel in the cylinder is higher in the orange case compared to the red one. And that means when then this amount of fuel all of a sudden ignites, we have a much greater fuel amount that immediately kind of explodes. And this can be seen at the bottom chart. You see at the beginning, at -20 degrees, it's just a natural compression line. So basically it's the compressed air, the air that gets compressed by the piston that creates the pressure. And then we see that the red line starts at a higher level compared to the orange one. This is simply because the combustion starts earlier. That explains why the red line at around -10 degrees is higher. And then all of a sudden, much later, I would say -8 degrees, we see that pressure rise on the orange line. We also see that it's much steeper compared to the red one. And this is, like I said, because all of a sudden we have a higher mass of unburned fuel igniting suddenly, whereas in case of the red fuel, we always keep steadily injecting more and more and more. And since it starts burning earlier, we do not all of a sudden ignite that great amount of fuel. This case, still not a problem because it is not really concerning for the engine, but you've probably heard of knocking. Knocking is a similar incident where the pressure, the ignition delay is much greater. It means you have an even bigger fuel mass already in the cylinder, and then you have this very more or less vertical pressure rise that can really lead to severe mechanical damage of the engine. So that explains hopefully a little bit the ignition delay situation, or the effect on the mechanical side of the engine. And then also, of course, if we think about the time, right? So we are running at 60 Hertz engine, 1800 RPM. The combustion basically only has time from closing of intake air valve to opening of exhaust valve to happen. It means if we start the combustion earlier, we simply have a little bit more time to finish the combustion. That helps us with the performance because more chemically bound energy can be transformed into mechanical energy. And then also it helps us with the emissions because they have more time to oxidize inside the cylinder, which explains a little bit emission advantages we're going to see in a minute. Brian, does that explain the cetane number definition a little bit?
I've actually never heard the cetane topic explained as well as you have done. I really understand that. It makes a lot of sense as to how what's going on inside the cylinder, and looking at both the thermal and the pressure charts here really clear things up. But like you said, this all ties back to emissions. And I know that you've done some testing on this as a R&D expert. Let's dive into what have you seen when you've tested this and really focus on the emissions. So when I look at the actual unit, what are the emissions coming out of it? Do they change? Do they not change? What have you seen?
Yeah, so we have actually done two studies. One was actually done in the field, and this is the first one where we are looking at. So we used mobile emission measurement equipment. They are not as precise as our lab grade equipment, but for comparability reasons, definitely good enough. So what the team has done here is it replicated the D2 cycle, which is the standard certification cycle for our power gen engines, 100% load, 75, 50, 25, and 10% load. And you can see here they ran it with, it says heating oil in Europe. Customers, commercial customers are allowed to use heating oil instead of gas station diesel, but it's again chemically similar. So, and they also used HVO, and I think the most impressive chart is top left corner. You can see the soot emissions dropped significantly using HVO. Top right, you see the NOx emissions, yeah, slightly lower, greatest advantages in the low load area at the 10% point. And then CO2 emissions, slightly lower, but I mentioned before, right, we're talking about decarbonization, we're trying to be CO2 neutral. This is maybe not the significant effect somebody would expect when we're talking about 90, 100% CO2 reduction. And again, we are burning a hydrocarbon fuel, so we are always going to be emitting CO2 emissions. That's why we need to look at the entire life cycle of the fuel, and we're going to talk about that in a minute. The CO2 advantage can simply be explained because the C/H ratio of HVO is lower compared to the other one, so it simply has a little bit less C atoms or molecules in there. But this is really not the big advantage. I think the key for us, or the key news, is the emissions do not increase, which is good because that means our emission label is still valid. And in turn, and actually, most of the emissions we were measuring actually went down, and soot emissions most significant.
That is quite impressive.
Yeah. Yeah, and this just summarizes it. I mean, you can see here soot between 73 and 86%. This is massive. I mean, also just a quick disclaimer that cannot be just simply transferred to any other engine, because definitely the type of engine, the way the combustion works needs to be considered. But we're going to see later also that we confirmed these results in our lab, and we also, of course, read some papers from other researchers, and our experimental results are basically in line with theirs. So if you want to use HVO on your engine, it's been approved by your manufacturer, you should see similar trends, definitely. Yeah, Brian, these are the results of the second study we did. This was actually in our lab, so 1065 certified lab. And we ran exactly the same. So D2 cycle with HVO and ULSD. Here at the top, I do not have the individual results of all 5 cycle points. This just shows the weighted average of the total cycle. And on the right upper corner, you can see the soot, or in this case, we measured gravimetric PM emissions. Significant reductions. I'm sorry, the The scaling is a little bit misleading because it looks like the NOx emission reduction was actually greater than the PM, but it's not true because you see we come down on the NOx side from 4.6 to maybe 4.35, whereas on the PM side we come down from almost 120 milligrams to 80. So lab test confirmed the field test, and of course we also measured fuel consumption because that is equally important, I'd say. And here you can now see the difference that I mentioned before when we compare the heating value in terms of megajoule per kilogram versus megajoule per liter, or per mass versus volume, basically. Left bottom is the specific fuel consumption as we know it in grams per kilowatt hour. And it's not a surprise since HVO has the better heating value and it has better combustion efficiency because of the higher cetane number. We see that HVO has lower specific fuel consumption. But now if we look at the chart on the right side, again, we see the density disadvantage of HVO. So we can see that in this case, actually, the fossil diesel has a slight advantage over HVO fuel. And like I mentioned,
I'd like to talk to you if we need to change how we do our fuel sizing, if we should do it more like the airplanes where we do it by weight, or if we should keep volume. But that's a whole nother webinar, a whole nother discussion. But you said we had some data based upon other sources just to kind of look at that. What do we got?
Yeah, so it's not a coincidence or just luck that it works that well with our engines. Other researchers basically found the same results. This is a paper I found, automotive study here at full load. And please just focus on the black and the orange lines. They also did, of course, some additional testing. So you can see red is our fossil diesel fuel, orange is the HVO fuel, and again, top left corner, soot emissions, and you can see all across the board the orange line is below the black line, basically confirms the soot reduction that we have seen as well. And so this was the full load result, and I think they did the same for part load points. And the chart looks now a little bit different, the one on the left side, because here it's soot over NOx emissions. But again, you can see at constant NOx, 2 gram, 3 gram, 4 gram, 5 gram, the orange line is always below the black line. So again, at same NOx, specific NOx emissions, you will always have lower HVO emissions. And this is basically what confirms our findings and also findings of the competition. So much about emissions. So good news is we do not see any disadvantages. We don't see any risk for existing tier 2 labels, for example. However, especially in power gen, Brian, you mentioned it, it's equally important that we still can maintain 100% power. And I think you have some slides that will tell us a little bit more about that.
Yeah, no, that's very key. And so what I like to do is mentally take these two charts that I'm showing and really just lay them mentally over top of each other. At the top, you have basically the voltage deviation or the voltage dips. And when you slide these over each other, you basically see that they're almost identical. So when we add on a 25, a 50, a 75, or 100% load step, we're going to end up with basically the exact same voltage dip characteristic. So what that means is when I use this fuel in an application, how I sized my unit and how it's going to behave when I turn on a load or turn off a load is going to be almost identical. You'll really hardly notice the difference between that of what it does on diesel fuel and what it does on HVO. So that really helps out the drop-in behavior of the fuel. And then you also, at the bottom, you see the power chart. So basically, how much power did we get from the unit? Now, understand this is like what Jens said. This is what we did on our engine and things of that sort. That's not unique to every single engine out there in the world. We can only speak about ours. And we saw the same power capabilities out of it. So we could get full load power out of that same unit without making any modifications to it. So Jens, maybe a little pat on the back for all the hard work that you guys do over at the R&D facility. I do appreciate it. You make my life super easy. I'll have to get you a beer or something at some time, but keep up the good work on that.
I'll remind you next time something goes wrong.
Fair enough. And when we look at the fuel consumption between the two, and this is just during operation, so we showed it in those other charts, but we did the same thing on a complete genset just to kind of validate the whole system. And yeah, you do see the little bit of a difference that we talked about, but nothing super drastic that we really had to worry about on that. And then, talk a little bit about the overall emissions. We do have to kind of speed up to make sure we get time for questions.
Yeah, definitely. So now we want to talk a little bit about the decarbonization approach of HVO. Why do we actually see this as a chance to transition to carbon neutral fuels? As we've seen at on the slide with the engine out emissions, there is still significant CO2 emissions. So we have to find a way to reduce the CO2 emissions differently, and therefore we're going to look at the well-to-wheel calculation of a synthetic fuel. So this is not exactly HVO. This is just a study we found. And also, please don't get confused by the units. It's a European study, so it's in kilometers and grams. But I think just to bring across the point, it's a very helpful graphic. And so, yeah, it basically starts on the left side with the feedstock. And since it's an organic feedstock, it's a plant. It absorbs CO2 while it's growing because it needs CO2 for photosynthesis. So we need to keep that in mind because later we'll see we're going to get basically a credit for the CO2 the plant absorbs before it's being harvested. And then when we look at the whole life cycle, right, we need to seed the feedstock, we need to fertilize it, we need to harvest it. That could all cause some CO2 emissions. So you see in the study, they found 4.4 grams CO2 per megajoule. Then the harvested feedstock is being transported to the factory where it's then being processed. In this case, it's an ethanol fuel, but it doesn't matter. And then later, the fuel needs to be transported to the gas station. So in this study, this entire process caused an additional 29 grams of CO2 emissions. So now this is in this calculation being settled with the CO2 credit we got from the plant basically absorbing CO2 before it was harvested. In this case, you can see it was 71.4 grams. So means once the fuel hits the gas station, it comes in with a CO2 credit basically of minus 42.4 grams per megajoule. Now, please don't get confused. The 73.5 on the right side is exactly the same as the 42.4. Now it's just being converted from CO2 per megajoule to CO2 per kilometers for this car example that's being used. And so now what happens is just our regular combustion process. We're burning a hydrocarbon fuel, so we're emitting CO2 emissions. The engine they used in this study emitted 124.3 grams. This is being offset with the minus 73.5, which leaves us with a total, in that case, of 50.8. Would we not have gotten this CO2 credit from this organic feedstock, it would have been the 124.3 plus whatever the 29 gram per megajoule are in CO2 per kilometer. So significantly higher compared to what we got out of here. And so when you look at the whole process, we already see there's maybe room for improvement when we look at the 29 grams of CO2 that are being emitted during the production and transportation process. And this is also something that is important when we talk about HVO. Not every HVO is exactly similar to other HVOs because it really depends on the feedstock and the production process. And I think, Brian, we have a slide that explains that a little bit better. Yes, perfect. Because I mentioned at the beginning, during the introduction, that the most beneficial feedstock is actually the waste cooking oil. And if you look at the lower chart, on the right side, we have the two feedstocks for HVO, basically waste cooking oil or tallow. And you can see the y-axis is the CO2 emissions again per megajoule. And you see here these two fuels or HVO derived from these two feedstocks only has a carbon footprint basically between, I would say, 10 to maybe 25 grams CO2 per megajoule. Whereas you can see the other HVO fuels are somewhere between, let's say, 50 to 70. And you can see the biggest difference is the red bar, because the two on the right side, they have no red bar, whereas all the other ones have one, and that's production and conditioning at the source. So that if there is room for improvement, or if that can be optimized, we can also lower the CO2 footprint of the HVO derived from other feedstocks. So now if we compare that, just 1 second, to diesel and gasoline, the upper right chart shows us the carbon footprint of diesel and gasoline. You can see here it's 87, 89 roughly. So that means even if we compare it to our worst HVO, which is somewhere in the 70 area, we still have an advantage. If we compare it to the best, it is significant. And that's why comparing the fuels in this study, you can find CO2 benefits between 33 and 94%. So not 100% CO2 neutral, but compared to fossil fuel, significant reduction.
That's really good to know. It depends on the source as to where we get it from. I want to talk a little bit about some of the challenges, and I might answer some of the questions because I peeked over at some of them, and your questions are related to the challenges that I wanted to talk about. And it's related to the availability. Like with any new fuel, it's not just readily available in mass quantities. There's a lot of production about it, but we can't switch everything over right onto this fuel. It's no different than any other renewable fuel that we have that limitation. It will continue to rise, and here's some charts just to kind of show you the historic behavior. Also, another question is often, well, what does this cost? And a lot of it depends on government incentives, or basically the carbon credits and what we can get for it. Typically, we see ranges anywhere from $5 to $15 a gallon, and that's in the United States is what we're kind of looking at from that perspective. On the higher end, usually that's also including the transportation cost, because you may have to ship it across multiple states maybe to get it to your location, just because it's currently not set up closely located to where you're located. The other thing that I want to kind of look at is where's the future going, and what's everything looking at? We see the biggest growth really in the United States, or also in South America, to where production will go up drastically. And really what we see by 2025, when we look at this from a global perspective, about a factor of 4 based upon the 2020 standards. And when we look at where are these fuels coming from, things of that sort, most of it in the United States, and just really looking at that alone, because I know there's a question related to that, is it's on the West Coast. So that's where currently it's coming in. That's where the biggest credits are. We fully expect that to change over time, but that is where that's limited at today. So we talked about a lot of different things. I'm going to hit this quick because I want to leave some time for questions. We have the reduction of pollutants. We have the long-term storage, the positive chemical characteristics with the cetane improvements. We get the same performance. It is a drop-in fuel that we can use today. Please do talk to your engine manufacturer before you just use it. Just my little caveat there. We have the well-to-wheel emission characteristics. And Gary, I'm going to pass it back to you. I'm hoping we didn't use too much time and you can ask a few questions.
Got it. Thank you so much. Yeah, we will now take a couple of questions from the audience. If you have questions, please type them into the Ask a Question box on your screen. We'll get to as many as we can. Questions that we don't get to, here's the good part, will be posted online at www.csemag.com. That's csemag.com with the archive version of this webcast. And remember to download a certificate of completion or a copy of the presentation. Please use the event resources tab on the left-hand side of your screen. So guys, I think we'll only have time for one or two questions here. I'm going to start with the most basic. Where specifically can I get HVO?
I'll take the first go at that one. We find it readily available over on the western coast of the United States. You can get this from a couple of manufacturers. Reach out to your fuel company that you currently work with or your fuel supplier. Tell them that you're looking for HVO. If you have struggles, things of that sort, feel free to reach out to us and we can try to help you out as best as we can. I know, Jens, you've had some hurdles in getting it to your test bench, but that was when HVO was kind of at the cutting edge, and it's improved since then. But it's possible to get in all of the United States is what we've found. It's just, what is it going to cost and what hurdles do you have to get over with that?
That makes sense. When using HVO, what do I need to do to get the unit ready to run on it?
First and foremost, talk to your engine manufacturer. Make sure that your engine can run and operate on this. Just because it's good on one engine, I can't promise that it's good on every other engine. That's just the caveat of the nature of the chemistry behind things. But to oversimplify it, it is a drop-in fuel, and we talked about that. What does that mean? You add it to your tank. You don't have blending requirements. So if you need to add 5 gallons, you can top off with 5 gallons. If you need to replace the whole tank with new fuel because it's empty, you can do that. It's because it's so much like diesel, it blends right into there as a drop-in fuel. That's the beauty of this.
You've covered a little bit of this in your talk, but I'll ask the bigger question. What are some of the sustainability benefits of HVO?
Jens, do you want to take that one?
Well, the biggest one, obviously, it's based on or made of or organic feedstock. So as long as we as a society do our job and make sure that we do not consume more than we can produce or grow, and we do not create a competition between our vehicles or our tank versus what we want to eat or what animals need to be fed. This is definitely the greatest sustainability advantage of HVO over fossil fuel, where we cannot influence basically the growth. Brian, anything to add from your side?
I think that's a great way to look at it. And then when you look at the well-to-wheel emissions, that just shows that it's all part of that. We keep it within that carbon cycle, especially when we use already used oil. So like waste oil, for example, we just find a way to reuse something that we've already used, get more use out of something.
Yeah, maybe one point to add, I think, which we hadn't touched on when we're talking about all these synthetic fuels. We always need hydrogen to create them, and we know it needs a lot of energy to produce hydrogen, for example, through electrolysis. And the more renewable fuels we use to generate that hydrogen, the greener, of course, our solution is going to be.
Yeah, good point.
That makes perfect sense. Gentlemen, I hate to do this, but I think we're out of time. This could go on for a long time, but thank you everyone for all the great questions. And thank you again to our great speakers, Brian Ponstein and Jens Engelhardt, for sharing their time and expertise.
It was a pleasure. Thank you, Gary.
I'd also like to extend a special thanks to our sponsor, MTU, a Rolls-Royce solution, for sponsoring today's event. Now that we are just about done, we're not quite done, we do want to hear how we did. An exit survey will pop up on your screen as soon as this webcast ends. Please take a moment to complete it because we use this information to improve our future webcasts. Finally, on behalf of Consulting Specifying Engineer and CFB Media, I'd like to thank you for attending. This concludes our webcast. Thank you, everyone. Have a great day.